Antoine Lavoisier.
Antoine-Laurent de Lavoisier was a French nobleman and chemist central to the 18th-century chemical revolution and a large influence on both the histories of chemistry and biology. He is widely considered to be the father of modern chemistry. It is generally accepted that Lavoisier's great accomplishments in chemistry largely stem from the fact that he changed the science from a qualitative to a quantitative one. Lavoisier is most noted for his discovery of the role oxygen plays in combustion. He recognized and named oxygen, 1778, and hydrogen, 1783, and opposed the phlogiston theory. Lavoisier helped construct the metric system, wrote the first extensive list of elements, and helped to reform chemical nomenclature. He predicted the existence of silicon, 1787, and was also the first to establish that sulfur was an element, 1777, rather than a compound. He discovered that, although matter may change its form or shape, its mass always remains the same. Lavoisier was an administrator of the Firme Générale and a powerful member of a number of other aristocratic councils. All of these political and economic activities enabled him to fund his scientific research. At the height of the French Revolution, he was accused by Jean-Paul Marat of selling adulterated tobacco and of other crimes, and was eventually guillotined a year after Marat's death.
Biography. Early life and education.
Antoine-Laurent Lavoisier was born to a wealthy family in Paris on August 26, 1743. The son of an attorney at the Parliament of Paris, he inherited a large fortune at the age of 5 with the passing of his mother. Lavoisier began his schooling at the Collège des Quatre Nations, known as the Collège Mazarin, in Paris in 1754 at the age of 11. In his last 2 years, 1760 to 1761, at the college his scientific interests were aroused, and he studied chemistry, botany, astronomy, and mathematics. In the philosophy class he came under the tutelage of Abbé Nicolas Louis de la Caille, a distinguished mathematician and observational astronomer who imbued the young Lavoisier with an interest in meteorological observation, an enthusiasm which never left him. Lavoisier entered the School of Law, where he received a bachelor's degree in 1763 and a licentiate in 1764. Lavoisier received a law degree and was admitted to the bar, but never practiced as a lawyer. However, he continued his scientific education in his spare time.
Early scientific work.
Lavoisier's education was filled with the ideals of the French Enlightenment of the time, and he was fascinated by Pierre Macquer's Dictionary of Chemistry. He attended lectures in the natural sciences. Lavoisier's devotion and passion for chemistry were largely influenced by Étienne Condillac, a prominent French scholar of the 18th century. His first chemical publication appeared in 1764. From 1763 to 1767, he studied geology under Jean-Étienne Guettard. In collaboration with Guettard, Lavoisier worked on a geological survey of Alsace-Lorraine in June 1767. In 1764 he read his first paper to the French Academy of Sciences, France's most elite scientific society, on the chemical and physical properties of gypsum, hydrated calcium sulfate, and in 1766 he was awarded a gold medal by the king for an essay on the problems of urban street lighting. In 1768 Lavoisier received a provisional appointment to the Academy of Sciences. In 1769, he worked on the first geological map of France.
Firme Générale and marriage.
At age 26, around the time he was elected to the Academy of Sciences, Lavoisier bought a share in the Firme Générale, a tax farming financial company which advanced the estimated tax revenue to the royal government in return for the right to collect the taxes. Lavoisier attempted to introduce reforms in the French monetary and taxation system to help the peasants. While in government work, he helped develop the metric system to secure uniformity of weights and measures throughout France. Lavoisier consolidated his social and economic position when, in 1771 at age 28, he married Marie-Anne Pierrette-Paulze, the 13-year-old daughter of a senior member of the Firme Générale. She was to play an important part in Lavoisier's scientific career, notably, She translated English documents for him, including Richard Kirwan's essay on phlogiston and Joseph Priestley's research. In addition, she assisted him in the laboratory and created many sketches and carved engravings of the laboratory instruments used by Lavoisier and his colleagues for their scientific works. Madame Lavoisier edited and published Antoine's memoirs. Whether any English translations of those memoirs have survived is unknown as of today, and hosted parties at which eminent scientists discussed ideas and problems related to chemistry. For 3 years following his entry into the Firme Générale, Lavoisier's scientific activity diminished somewhat, for much of his time was taken up with official Firme Générale business. He did, however, present one important memoir to the Academy of Sciences during this period, on the supposed conversion of water into earth by evaporation. By a very precise quantitative experiment, Lavoisier showed that the earthy sediment produced after long continued reflux heating of water in a glass vessel was not due to a conversion of the water into earth but rather to the gradual disintegration of the inside of the glass vessel produced by the boiling water.
Oxygen theory of combustion.
During late 1772 Lavoisier turned his attention to the phenomenon of combustion, the topic on which he was to make his most significant contribution to science. He reported the results of his first experiments on combustion in a note to the Academy on October 20, in which he reported that when phosphorus burned, it combined with a large quantity of air to produce acid spirit of phosphorus, phosphoric acid, and that the phosphorus increased in weight on burning. In a second sealed note deposited with the Academy a few weeks later, November 1, Lavoisier extended his observations and conclusions to the burning of sulfur and went on to add that, what is observed in the combustion of sulfur and phosphorus may well take place in the case of all substances that gain in weight by combustion and calcination, and I am persuaded that the increase in weight of metallic cases is due to the same cause.
Joseph Black's fixed air.
During 1773 Lavoisier determined to review thoroughly the literature on air, particularly fixed air, and to repeat many of the experiments of other workers in the field. He published an account of this review in 1774 in a book entitled Opuscules physiques et chimiques, Physical and Chemical Essays. In the course of this review he made his first full study of the work of Joseph Black, the Scottish chemist who had carried out a series of classic quantitative experiments on the mild and caustic alkalis. Black had shown that the difference between a mild alkali, for example, chalk, CaCO3, and the caustic form, for example, quicklime, CaO, lay in the fact that the former contained fixed air, not common air fixed in the chalk, but a distinct chemical species, carbon dioxide, CO2, which was a constituent of the atmosphere. Lavoisier recognized that Black's fixed air was identical with the air evolved when metal cases were reduced with the charcoal and even suggested that the air which combined with metals on calcination and increased the weight might be Black's fixed air, that is, CO2.
Joseph Priestley.
In the spring of 1774 Lavoisier carried out experiments on the calcination of tin and lead in sealed vessels which conclusively confirmed that the increase in weight of metals on calcination was due to combination with air. But the question remained about whether it was combination with common atmospheric air or with only a part of atmospheric air. In October the English chemist Joseph Priestley visited Paris, where he met Lavoisier and told him of the air which he had produced by heating the red coal of mercury with a burning glass and which had supported combustion with extreme vigor. Priestley at this time was unsure of the nature of this gas, but he felt that it was an especially pure form of common air. Lavoisier carried out his own researches on this peculiar substance. The result was his famous memoir on the nature of the principle which combines with metals during their calcination and increases their weight, read to the Academy on April 26, 1775, commonly referred to as the Easter Memoir. In the original memoir Lavoisier showed that the mercury coal was a true metallic coal and that it could be reduced with charcoal, giving off Black's fixed air in the process. When reduced without charcoal, it gave off an air which supported respiration and combustion in an enhanced way. He concluded that this was just a pure form of common air, and that it was the air itself undivided, without alteration, without decomposition, which combined with metals on calcination. After returning from Paris, Priestley took up once again his investigation of the air from mercury cool. His results now showed that this air was not just an especially pure form of common air but was 5 or 6 times better than common air, for the purpose of respiration, inflammation, and every other use of common air. He called the air dephlogisticated air, as he thought it was common air deprived of its phlogiston. Since it was therefore in a state to absorb a much greater quantity of phlogiston given off by burning bodies and respiring animals, the greatly enhanced combustion of substances and the greater ease of breathing in this air were explained.
Easter Memoir.
The official version of Lavoisier's Easter Memoir appeared in 1778. In the intervening period Lavoisier had ample time to repeat some of Priestley's latest experiments and perform some new ones of his own. In addition to studying Priestley's dephlogisticated air, he studied more thoroughly the residual air after metals had been calcined. He showed that this residual air supported neither combustion nor respiration and that approximately 5 volumes of this air added to 1 volume of the dephlogisticated air gave common atmospheric air. Common air was then a mixture of 2 distinct chemical species with quite different properties. Thus when the revised version of the Easter Memoir was published in 1778, Lavoisier no longer stated that the principle which combined with metals on calcination was just common air but nothing else than the healthiest and purest part of the air, or the eminently respirable part of the air. In the following year Lavoisier coined the name oxygen for this constituent of the air, from the Greek words meaning acid former. And Considerations Generales sur la nature des acides, General Considerations on the Nature of Acids, 1778, he was struck by the fact that the combustion products of such known metals as sulfur, phosphorus, charcoal, and nitrogen were acidic. He held that all acids contained oxygen and that oxygen was therefore the acidifying principle.
Dismantling phlogiston theory.
Lavoisier's chemical research between 1772 and 1778 was largely concerned with developing his own new theory of combustion. In 1783 he read to the Academy his famous paper entitled Réflexions sur la phlogistique, Reflections on Phlogiston, a full-scale attack on the current phlogiston theory of combustion. That year Lavoisier also began a series of experiments on the composition of water which were to prove an important capstone to his combustion theory and win many converts to it. Many investigators had been experimenting with the combination of Henry Cavendish's inflammable air, which Lavoisier termed hydrogen, Greek for water former, with dephlogisticated air, oxygen, by electrically sparking mixtures of the gases. All of the researchers noted the production of water, but all interpreted the reaction in varying ways within the framework of the phlogiston theory. In cooperation with mathematician Pierre-Simon de Laplace, Lavoisier synthesized water by burning jets of hydrogen and oxygen in a bell jar over mercury. The quantitative results were good enough to support the contention that water was not an element, as had been thought for over 2,000 years, but a compound of 2 gases, hydrogen and oxygen.
Gunpowder Commission.
Lavoisier's researches on combustion were carried out in the midst of a very busy schedule of public and private duties, especially in connection with the Ferme Generale. There were also innumerable reports and committees of the Academy of Sciences to investigate specific problems on order of the royal government. Lavoisier, whose organizing skills were outstanding, frequently landed the task of writing up such official reports. In 1775 he was made one of 4 commissioners of gunpowder appointed to replace a private company, similar to the Ferme Generale, which had proved unsatisfactory in supplying France with its munitions requirements. As a result of his efforts, both the quantity and quality of French gunpowder greatly improved, and it became a source of revenue for the government. His appointment to the Gunpowder Commission brought one great benefit to Lavoisier's scientific career as well. As a commissioner, he enjoyed both a house and a laboratory in the Royal Arsenal. Here he lived and worked between 1775 and 1792.
Pioneer of stoichiometry.
Lavoisier's researches included some of the first truly quantitative chemical experiments. He carefully weighed the reactants and products of a chemical reaction in a sealed glass vessel, which was a crucial step in the advancement of chemistry. In 1774, he showed that, although matter can change its state in a chemical reaction, the total mass of matter is the same at the end as at the beginning of every chemical change. Thus, for instance, if a piece of wood is burned to ashes, the total mass remains unchanged. Lavoisier's experiment supported the law of conservation of mass. In France it is taught as Lavoisier's law and is paraphrased from a statement in his Traité élémentaire de chimie to rien ne se perd, rien ne se crée, tout se transforme. Nothing is lost, nothing is created, everything is transformed. Mikhail Lomonosov, 1711–1765, had previously expressed similar ideas in 1748 and proved them in experiments. Others whose ideas predate the work of Lavoisier include Jean Rey, 1583–1645, Joseph Black, 1728–1799, and Henry Cavendish, 1731–1810. See an historical note on the conservation of mass.
Chemical nomenclature.
Lavoisier, together with L.B. Guyton de Morviat, Claude Louis Berthelot, and Antoine-François de Fourcroy, submitted a new program for the reforms of chemical nomenclature to the Academy in 1787, for there was virtually no rational system of chemical nomenclature at this time. The new system was tied inextricably to Lavoisier's new oxygen theory of chemistry. The classical elements of earth, air, fire, and water were discarded, and instead some 55 substances which could not be decomposed into simpler substances by any known chemical means were provisionally listed as elements. The elements included light, caloric, matter of heat, the principles of oxygen, hydrogen, and azote, nitrogen, carbon, sulfur, phosphorus, the yet unknown radicals of muriatic acid, hydrochloric acid, boracic acid, and fluoric acid. 17 metals. 5 earths, mainly oxides of yet unknown metals such as magnesia, borite, and strontia. 3 alkalis, potash, soda, and ammonia. And the radicals of 19 organic acids. The acids, regarded in the new system as compounds of various elements with oxygen, were given names which indicated the element involved together with the degree of oxygenation of that element, for example sulfuric and sulfurous acids, phosphoric and phosphorus acids, nitric and nitrous acids, the ic termination indicating acids with a higher proportion of oxygen than those with the use ending. Similarly, salts of the ic acids were given the terminal letters 8, as in copper sulfate, whereas the salts of the use acids terminated with the suffix ite, as in copper sulfate. The total effect of the new nomenclature can be gauged by comparing the new name copper sulfate with the old term vitriol of Venus. Lavoisier described the system of nomenclature in Méthode de nomenclature chimique, Method of Chemical Nomenclature, 1787.
Elementary treatise of chemistry.
Lavoisier employed the new nomenclature in his Traité élémentaire de chimie, Elementary Treatise on Chemistry, published in 1789. This work represents the synthesis of Lavoisier's contribution to chemistry and can be considered the first modern textbook on the subject. The core of the work was the oxygen theory, and the work became a most effective vehicle for the transmission of the new doctrines. It presented a unified view of new theories of chemistry, contained a clear statement of the law of conservation of mass, and denied the existence of phlogiston. This text clarified the concept of an element as a substance that could not be broken down by any known method of chemical analysis, and presented Lavoisier's theory of the formation of chemical compounds from elements. It remains a classic in the history of science. While many leading chemists of the time refused to accept Lavoisier's new ideas, demand for Traité élémentaire as a textbook in Edinburgh was sufficient to merit translation into English within about a year of its French publication. In any event, the Traité élémentaire was sufficiently sound to convince the next generation.
Physiological work.
The relationship between combustion and respiration had long been recognized from the essential role which air played in both processes. Lavoisier was almost obliged, therefore, to extend his new theory of combustion to include the area of respiration physiology. His first memoirs on this topic were read to the Academy of Sciences in 1777, but his most significant contribution to this field was made in the winter of 1782-1783 in association with Laplace. The result of this work was published in a famous memoir, On Heat. Lavoisier and Laplace designed an ice calorimeter apparatus for measuring the amount of heat given off during combustion or respiration. The outer shell of the calorimeter was packed with snow, which melted to maintain a constant temperature of 0 degc around an inner shell filled with ice. By measuring the quantity of carbon dioxide and heat produced by confining a live guinea pig in this apparatus, and by comparing the amount of heat produced when sufficient carbon was burned in the ice calorimeter to produce the same amount of carbon dioxide as that which the guinea pig exhaled, they concluded that respiration was in fact a slow combustion process. Lavoisier stated, "La respiration is donc une combustion, that is, respiratory gas exchange is a combustion, like that of a candle burning." This continuous slow combustion, which they supposed took place in the lungs, enabled the living animal to maintain its body temperature above that of its surroundings, thus accounting for the puzzling phenomenon of animal heat. Lavoisier continued these respiration experiments in 1789-1790 in cooperation with Armand Seguin. They designed an ambitious set of experiments to study the whole process of body metabolism and respiration using Seguin as a human guinea pig in the experiments. Their work was only partially completed and published because of the disruption of the Revolution. But Lavoisier's pioneering work in this field served to inspire similar research on physiological processes for generations to come.
Final days and execution.
As the French Revolution gained momentum from 1789 on, Lavoisier's world inexorably collapsed around him. Attacks mounted on the deeply unpopular Ferme Generale, and it was eventually suppressed in 1791. In 1792 Lavoisier was forced to resign from his post on the Gunpowder Commission and to move from his house and laboratory at the Royal Arsenal. On August 8, 1793, all the learned societies, including the Academy of Sciences, were suppressed. It is difficult to assess Lavoisier's own attitude to the political turmoil. Like so many intellectual liberals, he felt that the ancien regime could be reformed from the inside if only reason and moderation prevailed. Characteristically, one of his last major works was a proposal to the National Convention for the reform of French education. He tried to remain aloof from the political cockpit, no doubt fearful and uncomprehending of the violence he saw therein. However, on November 24, 1793, the arrest of all the former tax-gatherers was ordered. He was branded a traitor by the convention under Maximilien de Robespierre during the Reign of Terror, in 1794. He had also intervened on behalf of a number of foreign-born scientists including mathematician Joseph Louis Lagrange, resulting in the granting to them of exceptions from a mandate stripping all foreigners of possessions and freedom. Lavoisier was tried, convicted, and guillotined on May 8, 1794 in Paris, at the age of 50. Along with his 27 co-defendants. According to a, probably apocryphal, story, the appeal to spare his life so that he could continue his experiments was cut short by the judge, La République n'a pas besoin de savants ni de chimistes. Le cause de la justice ne peut être suspendue. The Republic needs neither scientists nor chemists. The course of justice cannot be delayed. Lavoisier was convicted with summary justice of having plundered the people and the treasury of France, of having adulterated the nation's tobacco with water, and of having supplied the enemies of France with huge sums of money from the national treasury. Lavoisier's importance to science was expressed by Joseph Louis Lagrange, who lamented the beheading by saying, "Il n'y leur fallu qu'un moment pour faire tout cette tête, et cent ans put être ni suffiront pas pour en reproduire une semblable." It took them only an instant to cut off this head, and 100 years might not suffice to reproduce its like.
Post-mortem.
A year and a half after his death, Lavoisier was exonerated by the French government. When his private belongings were delivered to his widow, a brief note was included, reading to the widow of Lavoisier, who was falsely convicted. About a century after his death, a statue of Lavoisier was erected in Paris. It was later discovered that the sculptor had not actually copied Lavoisier's head for the statue, but used a spare head of the Marquis de Condorcet, the secretary of the Academy of Sciences during Lavoisier's last years. Lack of money prevented alterations from being made. The statue was melted down during the Second World War and has not since been replaced. However, one of the main lycées, high schools, in Paris and a street in the 8th arrondissement are named after Lavoisier, and statues of him are found on the Hôtel de Ville and on the façade of the Cour Napoleon of the Louvre. His name is one of the 72 names of eminent French scientists, engineers and mathematicians inscribed on the Eiffel Tower as well as on buildings around Killian Court at MIT in Cambridge, MAS. Lavoisier is listed among eminent Roman Catholic scientists, and as such he defended his faith against those who attempted to use science to attack it. Louis-Édouard Grimaud, author of the standard French biography of Lavoisier, and the first biographer to obtain access to Lavoisier's papers, writes the following.
Legacy.
Lavoisier's fundamental contributions to chemistry were a result of a conscious effort to fit all experiments into the framework of a single theory. He established the consistent use of the chemical balance, used oxygen to overthrow the phlogiston theory, and developed a new system of chemical nomenclature which held that oxygen was an essential constituent of all acids, which later turned out to be erroneous. Lavoisier also did early research in physical chemistry and thermodynamics in joint experiments with Laplace. They used a calorimeter to estimate the heat evolved per unit of carbon dioxide produced, eventually finding the same ratio for a flame and animals, indicating that animals produced energy by a type of combustion reaction. Lavoisier also contributed to early ideas on composition and chemical changes by stating the radical theory, believing that radicals, which function as a single group in a chemical process, combine with oxygen in reactions. He also introduced the possibility of allotropy in chemical elements when he discovered that diamond is a crystalline form of carbon. He was essentially a theorist, and his great merit lay in his capacity to take over experimental work that others had carried out, without always adequately recognizing their claims, and by a rigorous logical procedure, reinforced his own quantitative experiments, expounding the true explanation of the results. He completed the work of Black, Priestley and Cavendish, and gave a correct explanation of their experiments. Overall, his contributions are considered the most important in advancing chemistry to the level reached in physics and mathematics during the 18th century. Lavoisier's work was recognized as an international historic chemical landmark by the American Chemical Society, Académie des Sciences de l'Institut de France and the Société Chimique de France in 1999.